Hey guys, and welcome back to another video on the channel. In this video, we're going to be solving a Maths Olympiad question. So one of my mates sent me this video of this particular problem that I thought was pretty interesting, and I just wanted to go through how to pretty much solve it. So the particular problem we're going to be taking a look at today is 3 to the power of m minus 2 to the power of m is equal to 65. Now there's a previous video done on this particular question that my mate actually got this from, but I'm just going to go through pretty much how to solve it if you were given this and you got a bit stuck. Okay, so let's take a look. So in this particular process here, we need to make this pretty easy to solve. Now it's quite hard initially because, well, there's a minus here instead of a multiplication or a division, and we have a 3 to the power of m and a 2 to the power of m, so these aren't the same numbers. So even if we did change how this looked, we wouldn't be able to use index laws. So what we're going to do is we're going to take pretty much a property that is used for index laws though, to make them look similar and make this problem a bit easier. So in other words, let's take a look at pretty much what happens with this index law. So if you have a to the power of n and you raise that to the power of m, that's going to be a multiplied by n times by m. So what we're going to do is we're going to change how both of these look. Now we've got to do it in a way such that it doesn't really change this number here. Do you agree if we raised, let's say we had 3 to the power of m and we raised it to the power of, let's say, 4 over 4, it wouldn't change it because 4 divided by 4 is still 1. So this would be valid if I wrote it like this. Now likewise, we can do the same for this entire thing here and the same here. But what we want to do is we're going to do this all to the power of 2 over 2. Now the reason we're going to do that is we're going to take advantage of this particular law here. So let's just do that. So if we took all this, so 3 to the m, and raised it to the power of 2 over 2, and we subtracted and we raised all this to the power of 2 over 2, but we left the 65 by itself, let's say. So this is a valid statement. What we're going to do is pretty much we're going to do the opposite of what we're going to do. Well, we're only going to take the top of number here and put it inside here. The reason we're going to do this, actually no, not the top number, sorry, the bottom number. We're going to take the bottom number and put it in here, because the reason we're going to do this is we're going to get an expression for a difference of squares. So this, if we can get an expression for difference of squares, it'll make this problem so much easier to solve. So in other words, we're going to basically, alright, we can move, this is the same as 2 over 2 is the same as 2 times by 1 over 2. So what we can do is effectively move this power of 1 over 2 inside here via this index law here. So if we do that, we can rewrite the line as 3 to the power of m over 2 all squared minus 2 to the power of m over 2 all squared is equal to 65. Okay, cool. And now what we're going to do, we can see we've almost got a difference of squares here, but to make things cleaner, we're going to replace this and this with variables. So I'm going to let 3 over m to the 3 to the power of m over 2 equal a. And I'm going to let this here, 2 to the power of m over 2 equal b. Now the reason I'm going to do this is because then I'll have pretty much a difference of squares. So I'm going to move all of this up here just so I have enough room. So what I effectively have now is pretty much a squared minus b squared is equal to 65. Now you're probably thinking, this hasn't really changed the question. Well, it has. It's made it a lot easier, because this here is a difference of squares clearly seen. So if you have, let's say, x squared minus y squared, this can be written as a plus y multiplied by x minus y. So if you were to do FOIL on this, this would be x squared minus xy plus xy plus, minus y squared. That would cancel and you would be left with the left hand side here. So this is a difference of squares. Now the reason we want to do this is we're going to break it up into pretty much a product of these two numbers. So in other words, if we replace this, this is going to be a plus b multiplied by a minus b. Now, you're probably thinking, why have we done this? Well, we've actually got an expression for two numbers multiplying by each other to get 65. And we know something about these numbers. We know this number has to be these two numbers plus together and these two numbers minus together. Now, let's look at the factors of 65 that are whole numbers. So 65, what can we express that as products? That's the same as 1 times 65. And we know that 65 minus 1 isn't going to be, so let's take a look at the possibilities here. If we put 65 in here times by 1, yes, that would satisfy that equation, but it wouldn't satisfy our little relationship in here. So what are the other factors? Let's take a look. We can't do 4. Can we do 5? Yeah, we can. So this is the same as 13 times by 5, isn't it? So if we replace this here, so a plus b multiplied by a minus b is equivalent to 65, which is equivalent to 13 times by 5. Now you're probably thinking, righto, this looks like to be getting somewhere. So what we can actually do is, alright, we know this number here would be bigger than this number here. So we're going to say, alright, this here must be equivalent to 13. And we're going to say, alright, what else can we say? We can say this here must be equivalent to 5. So what we get is two linear equations. So we get a plus b is equal to 13, and then we get a minus b is equal to 5. And you can see we have two simultaneous equations here. And all we're going to do is add equation 1 and equation 2 together. So what we get is pretty much 2a is equal to 18. Therefore, a must be equal to 9. And if we substitute this back into here, we're going to get 9 plus b is equal to 13. So therefore, b must be equal to 4. Now, let's see if this satisfies it. 9 plus 4 is 13. That satisfies that one. And 9 minus 4 is 5, which satisfies that. So in other words, these are a and b. So a is 9 and b was 4. And we know what a and b are equal to. We know that a is equal to 3 to the power of m over 2 must be equal to 9, and 4 must be equal to 2 to the power of m over 2. Now we can see this looks really much easier to solve because 9 can be expressed in terms of a base 3 if you square it. So this is equivalent to, so 3 to the m or squared is actually equivalent, so 9 can be expressed as 3 squared, can't it? Same here with 4. 4 can be expressed as 2 squared. And as you can see here, because this is the same base, that means this here must be equivalent to this. So in other words, we have a little equation in here. So what we have here is m over 2 must be equal to 2. Therefore, m must be 4. So if we put m is equal to 4 into here, we'd get, alright, 2 to the power of 2 is equal to 4. And then we get 2 to the power of 2 is equal to 2 to the power of 2. So boom. The solution, m equals 4. And let's see if this works for our general solution. So if we had, right, so we're going to actually rub out some stuff. So let's move this stuff for a bit. So let's see if this works for our general equation here. So if we had 3 to the power of 4 minus 2 to the power of 4, what's this going to be? So 3 to the power of 4, if I put that in my calculator, that's going to be 81. And if I put 2 to the power of 4 into my calculator, that's going to give you 16. So 81 minus 16 is 65, which satisfies that. So m equals 4 is the only solution to this. Alright, I hope you enjoyed that video. Thank you so much for watching.